Well, I guess we're getting diminishing returns on the live attendance here.
Yeah.
Is it, well, it's still interviews now or? But that's-
It ended yesterday, I
Yeah,
think.
all right, so that's not it.
Yeah.
Early weekend, I guess, but. Anyway, just wanted to just keep going on this thing. So I wanted to find a paper on the packing length and I found, so I couldn't find, so anyway, let me go here. So if you look, like I figured out why, like no one's, so this is like all the publications that have like packing length in it. So it's like, and this is like up to 10 per year, and that's just like nothing really. So basically, it seems like it had a little burst around 2006 when Lou Fetters is a guy who kind of got this packing length idea going at ExxonMobil. And then there was a burst around then. So it invented in like, I guess in the 90s. I don't know what the 78 reference is. So anyway, there's almost no references to it, and it's diminishing. Right, so basically seems to be kind of it's kind of like a dying topic. So it's good to check, I guess. I mean, I did find it before I realized that. And also, let's see, what else is another slide here like that? Like the highest citation for this is Fetter's paper. And it's got like 400, which that's a lot, but it's not that much. Total's 3,000 for packing lights. So it's kind of, I don't know. The reason why I think it's a big thing is because Fetters won the Ford Prize for American Physical Society, which is like a high honor, like Nobel laureates have won it. And so it seemed like it came to prominence then. But basically, if you look at this, at how it's performed, it's kind of like less than stellar kind of performance. So I might just skip it next time, teach the class, But anyway, we're stuck with it. So I got this, so I couldn't find any paper 2023, even though this thing claims that there were like 5 papers and I guess that's 2022. No, it must be 2023. So anyway, I couldn't find any of those, but with a kind of a random search. So I did find one that's like a Nature paper, which is nice, but it's 2020, so it's like 4 years ago. And then this is by this guy Ralph Colby, who wrote that Polymer Physics book. I don't know if anyone's looked at that, but so he's kind of a prominent character from UPenn. And then so being at UPenn, he's kind of, ExxonMobil isn't that far from there. So I think he's probably had something to do with them. That might be why he's using the packing length here. I mean, his conclusion is the packing length doesn't work for this thing, what he's doing now. At least it doesn't work perfectly. So he invents something else to use. So what he's looking at is it's a paper about conjugated polymers, which are like conducting polymers. Like polyaniline was the first one, conductive polymers. So this is polyacetylene. So basically, when you have a double bond, so first everything's like coplanar with a double bond. So if you have conjugated, so double, single, double, then the entire molecule is in a plane. It's like fixed on a plane. It's a rigid structure, right? So anyway, also if you can dope this to kind of free up one of the electrons, so the electrons are automatically like jumping from that bond to that bond. So this is not really double, this is double single, and this is double single. So the electron has mobility along this chain. If you dope it, it's like a semiconductor. If you dope it, then you can get conduction, it'll conduct electricity. So polyaniline or polyacetylene is synthesized electrochemically, and you can it doesn't melt, you can't put it into solution or anything, so you can't process it. So you electrochemically can deposit it onto a surface, but you can't do much else with it. So people tried sticking things onto the side of it to make it soluble so you could process it. With limited success, I guess. Then other conjugated polymers were found, like these thiophenes. So thiophene is where like X is a sulfur, and polyaniline where you have a nitrogen here. It's like in the protein, in the peptides, we had like a double bond or a carboxyl group and an amine, and there was resonance between them. It's like the electrons would come over, and that's why it's a planar. So in the same way, you have an amine here, and it can do the same dance with a double bond here. So you can kind of get resonance with these double bonds if you put an amine here. And also you can put a thiol, a sulfur there. So basically, those are like the more processable conducting polymers, right? And then these are phenolines. So phenol would be an aromatic ring with an OH at the side. And if it's two of them, it's a phenolene has like two of those. And then if you put like an acetylene unit here, or polymerize this, acetylene would be 3, and then you polymerize it, it's 2. So if you put that in, then that becomes conjugated. So you have single, double, single. Then you can free up the electrons and it'll conduct electricity. Right. So that was around for a while, and then basically the processable conductive polymers were these two guys who are listed here someplace. McDermott was I think it was at University of Pennsylvania, and Heeger was at MIT, I think. I don't know if they still are. And then they had a bunch of postdocs. So there's people who are faculty that work with McDermott. And anyway, this is 77, right? So it doesn't seem like that long ago, but I was there, basically, it was a while ago. So we actually had a guy, Harry Mark, in the chemistry department who had a big lab, and he was pretty well known in this area, and he had worked with McDermott at Penn, I think. So anyway, he was also a NASCAR driver. It's like in his spare time, he raced NASCAR cars. And then he did this conducting polymer. It was kind of a hobby, more or less, So he went into his office, it was all like race car stuff in it. This was in whatever. What's the one? Not the tower, but the other building. Zimmer, I guess. It says Zimmer. No, Zimmer's a meeting hall. The other one, chemistry building. But anyway, he died, not in a car wreck. He died of something. I forget what. But anyway, so there is kind of linked to this conductive polymer business that you see. So anyway, so the problem is like in processability, because of the rigidity, this makes it improcessable. And it akin to like Kevlar is another one. So Kevlar is not conductive, but it kind of looks like, so Kevlar is a condensation polymer. So you have a phthalate, you have a double carboxylic acid, you replace it with Cl, then it condenses HCl out of this and make this polyamide. Like this is basically like a protein structure, the amine and the carboxyl. So this is a card between that carbon and oxygen, and the hydrogen, that's all planar. And then the aromatic ring is planar. And then you have a little, I think the whole molecule is conjugation goes to the NH also. So this thing looks like it would be conductive, but it's not a conductive polymer. I think, not sure why it's not a conductive polymer, but it isn't. Right? So, but what it is like super strong, right? So Kevlar is the bulletproof vest, and you can spin it into fibers and make like indestructible stuff with it, like sails and things for racing sailboats and stuff. It's expensive though, compared to other routes to get super strong, which you can do with polyethylene if you ultraamine, which is really cheap. So anyway, so Kevlar is like the battle helmets for the US Army, the green things that people wear. They're kind of bulletproof things. Also Kevlar was invented by a woman, so it's kind of weird in that sense. But somewhere there's a picture of it in here, I think, right here. Yeah. So I think at DuPont. But so anyway, it's in keeping with the like Carruthers condensation polymer expertise at DuPont. But anyway, so that's what they're looking at, and they want to know how to make these things processable. So in order to do it, you need to get above the glass transition. So if you're below glass transition, they're completely intractable, right? So they're kind of useless. And the idea is you're going to make flexible electronics with this. So you're going to coat the wires onto a sheet of plastic, and then you can make clothing that has conductivity to it. So you can make an electronic device. You can actually weave it with these kind of materials if you can get above the TG. So you have to have it above TG in order to use it, right? So anyway, so that's what they're doing. They're trying to figure out like what is it that makes this whole family of conductive polymers, conjugated polymers, flexible enough that you can process, you can use them in flexible electronics. So above the glass transition, so you need to know like a predictability of how you get flexibility in these things, like when you can get above TG. And they have, so in the classic way to do it, like I said, was just stick side groups onto polyaniline, then it makes it soluble, it makes it kind of more processable. The problem is when you add side groups onto it, you lose the conductivity. It's like a catch-22. The more flexible it gets, the less conductive it is. So there's kind of a balance, and he doesn't mention that feature here. He's just looking straight for glass transition. Right? So anyway, so he's got this whole slew of all the possible conductive polymers that have made, and Nobel Prize was linked to it. So it's kind of like there's a lot of them. There's more than what he has here, right? So there's any number of these conductive setups with thiols and aniline components in it, and some phenolines, and just stick them on any way that you could possibly do in a chemistry lab, and then just try different side groups. Right, so it's a trial and error process to find the perfect one for flexible electronics. So anyway, that's he says like that's not very tenable. So he says like I'm going to find a magic way to do this. So and they find a magic way. So they find this way, like they calculate this mobility, which isn't a real, it's not a mobility like a real number. It's a number that they made up, and they call it a mobility. So it's a number based on the structure that they can calculate that goes 1-to-1 with the glass transition with one free parameter. The free parameter being this thing A. So they have the A parameter here somewhere. So what they do is they write an equation that's got to do with the structure. It has only one free parameter A. Then they change A from 0.4 to 0.7. And then they find the mean square difference between the TG that they predict and the TG that actually the material has, right? And they find there's a sweet spot around 0.6 for A. And with that, they can predict the glass transition. Using that A in their equation, they can predict the glass transition like that, like almost perfectly for all this slew. Each dot here is a different material, right? So that's kind of sweet. It's kind of nice. And then when they predict, they compare their calculated TG with the experimental, they find 13-degree range, root mean square difference. Just it's not bad, especially when you look at. So the thing they compare it with is the packing length, which is like here. So the packing length isn't bad. Actually, it looks pretty good. So they say like take TG and the packing length, and you get a power law decay of roughly -3. Okay, so anyway. That's kind of interesting. They don't mention that on the paper, but the -3, if you look back to this guy, the notes, and you find so this is the storage modulus. So it's at low frequency, it's a liquid. Then you reach the rubbery plateau where it's a rubber, and then it goes into some other stuff about the rotation stuff out here. It's in a tube, so it flows again. That's the idea. So once you reach a tube diameter, then other things happen, right? So see, you have the rubbery plateau, that's the plateau modulus, and that goes with 1/p cubed, which is it's almost, he gets, like, he doesn't give the slope in this thing either, but basically I replotted this and figured out the slope is 3.3, -3.3. So it's almost identical to like this equation, which gives you, that equation gives you this plot, which is like the plateau modulus goes with p to the 1/3 somehow. Somehow that works out, but it's a cube root thing. So it doesn't look like, so basically this is the same dependence. So that means that the glass transition depends on the plateau modulus, which is, that itself is kind of weird, like, so why would the glass transition depend on the plateau modulus? And these things don't exactly have plateaus all the time. So he's measuring the glass transition with this dynamic rheology, right? So he's got, like, most of the time, so this is G prime is a solid, G double prime is a dash thing, right? And he sticks one of these conducting polymers in. So this is the TG is where you see a peak on this. So the peak means that you have like a Debye relaxer would be a Gaussian, have a Gaussian peak in this, meaning a single relaxation time. And the glass transition is where the molecules are stuck together because they can't move, and then you give it a little bit of free volume, and then all of a sudden they can move. So that when they move, there's a relaxation time associated with that. It's not so basically, if you wait forever when they're stuck together, they can eventually move out of the way, right? So infinity relaxation time, and then when you approach the glass transition, because the volume's expanding, then they're freed up. So that relaxation time reaches like normal time, like a second. And then you interact glass transition, and then above that it's flowing. It's a liquid, right? So anyway, so you have this peak in it. The peak reflects the frequency or temperature and the frequency by the Arrhenius dependence that's related to the flow, right? So that peak reflects that you have a Debye relaxer that flows there. So anyway, that gives it one relaxation time. But in these things, there's like two. There's another one down here, which he says is a side group motion, right? Like back when he showed the pictures of the things. That's a supplemental to it. But so he has the main chain, then he has these side groups on it, like C8H. So that's an octane side group. It's a iso octane. Actually, it would be iso whatever 16 is. Side group, right? So it's a huge side group. These are like the tails on the surfactants sticking off here, right? So anyway, that's the relaxation of that side group is a sizable contribution, and then the TG. And then he finds out. So the crux of this whole paper is that so he has a side group that's short, and then the TG. So these two relaxations, side group TG, main chain TG. And then if he makes a side group longer, that relaxation goes to a higher temperature. And at the same time, the TG relaxation moves to the left. So they start to merge at some point, right? So the two things are not independent. The side group, if it gets long, plasticizes the TG and shifts it to the left. So if you want to, and you want to shift it to the left, right? So you want to add longer and longer side groups. So you want to shift that further and further to the left so that you can get it to be a liquid above the glass transition at room temperature, and that's useful for flexible electronics. I mean, he doesn't mention that when you put longer and longer side groups on it, it doesn't conduct anymore. So it's no use to, but that's a feature he didn't mention. Didn't come out in a review of this thing, right? But so basically, the crux of this thing is add longer side groups so you can shift this around. But in fact, there's another plot that's the conductivity, and you find out that dies when you put long side groups on it, right? Partly because you're interfering with the conjugation, and also because, well, you're interfering with the conjugation. That's why, I guess. You're also changing you're changing the kind of ability of the chain to straighten out. And if you think about it, like if you make a conductive wire out of this, I mean, the chains have to kind of be oriented in the direction of electrical conduction, so when you put the side groups on, it messes up that orientation. So there's a lot of features that he skims over, because the Nature paper can only be 5 pages. Like it's a letter, right? So you can't, it's a communication, so it's still limited in the space. That's why they usually have these extensive, like, supplementals, that go on and on. But this one isn't really that big. So this whole paper, it looks like a 6-month effort, really. It isn't much. Like he did some dynamic rheology measurements, G prime, G double prime, and then he did a couple of DSC measurements. So he has the heat flow versus temperature, and then so that's kind of what happened here. And then he did this analysis, and he figured out this function. So he has. So he says at the beginning. Let's see. So let me just go through this thing. Kinetics, blah, blah, blah. Oh, he mentions that, let's see, what does he say? Too stiff, brittle, flexible devices, electronic. Let me just go through this. Oh, there's also this issue that if you get it too far above TG, then it'll crystallize, because they're rigid chains. So they want to just stack up, right? And then form a crystal. Well, if they form a crystal, it's useless, right? They have to be kind of amorphous. So you have to be exactly near TG in your operation range, right? Which is possible to do, but basically, if it gets too high, he says you get crystals, and also these things will form liquid crystals, which means, so there's one link here for liquid crystals. You see that here. So everything's going to be open place, but sorry, there's something about, if you don't know what liquid crystals are, you should glance at the wiki page and figure it out. So basically, it's going to be molecules that line up, and they can line up. Pneumatic means they line up kind of in a straight line, you know. It's like, hey, so kind of like a worm. Good to see you. You know, it's like, so pneumatic means they line up in a straight line. And you can also get cholesteric liquid crystals, and then you can get smectic liquid crystals, which are, so anyway, smectic means that they pneumatic means they go in a straight line, and smectic is like a twisting to the thing, and then cholesteric. Anyway, it's like three kinds of liquid crystals. So these polymers will form liquid crystals because they're rigid chains. I mean, we usually see liquid crystal like a liquid crystal display, which is a low molecular weight liquid crystal. The polymers form liquid crystals too. I mean, there's a lot of arguments that when polymers crystallize, so they go from this kind of dust bunny thing, and then they have to straighten out. So they have to go through a liquid crystal state before they get to a crystal. So there's a whole group of people that are making that argument, you know, and then there's people that are arguing against that. So it's like, it's a debating issue. Then the top place for liquid crystals is Kent State in Ohio, like near Akron. Right? So it's basically, Ohio has like kind of all the leaders in liquid crystals up there, I guess. It's not a huge field, you know. So basically, but they are the king of liquid crystal. Like Kent State's known as a liquid crystal kind of capital of the universe. So anyway, so what else is he doing here? So that there's some question about that business, and then brittlement, predicting. So he's saying that like people have tried to predict the glass transition of these polymers. This whole, you know, you have to wonder like how he got this into nature, because the topic is not of general interest really. You know, it's kind of, all right, they won a Nobel Prize in this area. The glass transition part of it, I would say this paper would be like in macromolecules, you know, or maybe like polymer, because it's really it's an applied thing looking at glass transition, and they use an empirical function to predict it. So it isn't like they're going to win the Nobel Prize for this. So it doesn't really belong in nature, I think, but it's hard to tell. But I give them credit for getting it into nature, however they did it. Anyway, so he says like TG, so he's talking about TG here. So the whole homework is kind of about TG, you know, more than, even though the packing length is kind of a topic. So measures, so he's saying like how to get the TG. So he says the Debye-Waller factor is one way. So Debye-Waller factors, when you do X-ray diffraction on crystals, and then you get a peak, and the peak has a breadth to it. Well, especially aluminum, because the atoms move quite a bit. So as you heat up aluminum, the peaks get broader and broader, right? So Debye-Waller came up with the idea that had to do with the kind of the atomics, the motion of the atoms in the crystal. It gets larger. So the mean squared displacement is U squared. It's usually called sigma squared. Gets larger as you get to higher temperature for aluminum, and for other, I mean, for all metals, for every crystal basically, but especially for aluminum, it's really observable. And then you can get that by fitting the peak to a Gaussian function in Q, the scattering vector. So it's like Q squared, U squared, exponential minus Q squared, U squared over 2 or whatever, like just a Gaussian.
You say it's a peak. What's on the y-axis?
Of angle, like Q. No, this is for just diffraction, you know. So you do diffraction at different temperatures, you get a peak. And you measure the width of the peak by doing a Gauss. The other way is the Biesheurer method, which gives you like a nano crystal size. This is more for if you have a perfect crystal that's huge, you know, and then you can do the diffraction on it and change the temperature, and the peak broadens, right? So it's called the Debye-Waller broadening. Anyway, so that gives you an idea of like the free volume of the system. But here he's talking about amorphous materials. It's not exactly clear how he's getting the Debye-Waller factor, except by a simulation. You know, we could get it, but basically that factor's got to do with the spacing of the atoms, as does the free volume, which can be measured with positron annihilation. So kind of an oddball technique to get something that gives off positrons you put it next to a material and somehow you get a detector for positrons and watch how they get destroyed or something. They fly around in the free volume of the material, and their lifetime depends on the space that they have, like the space that's between the atoms. Anyway, so the free volume is a standard theory for glass transition. In other words, when you below a certain free volume, you have a glass. Above a certain free volume, above that free volume, you have a liquid, right? So that idea has been around. There's also an idea kind of like that, which is this Linderman criteria, which is that if you figure out the atomic spacing of a crystal, like the A parameter in the crystal, and then when the deviation in that parameter reaches 10%, so if you can find out that that's expanding with temperature, when that reaches 10%, then the crystal melts. So that's like the melting point. So Linderman criteria for melting, which has something to do with free volume. I mean, they're all kind of connected together. He kind of bunches them up here, right? I mean, basically because he's got references that cite it in that way, you know. So I ask him there, like, what are these things? And there's some links that tell you if you want to look at it. So, I mean, all of them are relevant. They're useful to know. But anyway, so he's just saying, like, if you're in polymer science, then you should know this stuff straight off. Like he's assuming that, and actually nature, he's assuming everyone in the world should know what these things are straight off, which is kind of true. I mean, if you're, especially in materials, you should probably know like what those things are. So it's good to look at them once, like a one-line thing that kind of says roughly what you think it is, you know, is good enough. But motion and complex materials. So those are like semi-science based things. Like they aren't, I wouldn't call it real science, you know, like the free volume idea is just a concept. It isn't really something you can pick up, you know. So and basically the by broadening, there's a lot of, anyway, there's a lot of things you could say about like how real those things are. But so anyway, then he goes into like the never world, which is just like totally empirical, right? So basically group contribution is one. So that's something you'll see all over the place. So that's like the thing of last resort, I think I call it here. Group contribution, the method when you're desperate, then you go to group contribution, which means you're going to take like the components, like the chemical, especially in organic materials, and take all the groups that are in it, every possible group, aromatic group, methyl group, methylene group, thiols, amines. So each one has a number associated with, or several numbers, like a polarity, a volume of the molecule, coulombic interaction, right? So you can make like 3 columns at least, maybe 5. And then you want to know like what is going to be the melting point of this stuff. So you take all those numbers and somehow you correlate it back to the melting point, and you just have an equation where you add together the numbers and you get the melting point. So it's empirical.
Would be weighted by the relative amount.
Yeah, you weight it. So it's interesting. Okay, that's existed since like 1900, maybe before that, in the 1800s. This group contribution was invented by the Dutch. Dutch thermodynamics people invented the group contribution method. So it's popular there. A lot of times you'll see papers from the Netherlands that are like something with the group contribution. So they're happy to do that. And you'll see like desperate people all over the world using it, you know, because if you come up and there's no other answer, you just say, okay, I'm going to tabulate everything and I'm just going to get the answer and that's it. And I can use it to build a chemical factory or something, right? So it's not you wouldn't be proud using the group contribution method. It's kind of the thing, like you're admitting that you're totally desperate when you use it. Anyway, and he's using something like group contribution, but he's got like an improved group contribution has only one parameter, right? Which is, it's nice, you know. And then he talks about this quantitative structure property relationships. So there's a link to that. It's just the same thing. It's the same story, like find the groups, add them up. And then machine learning, which is kind of the same thing too. So these 3 things, so group contribution is 1880, maybe 50, maybe. And this QSPR is like the 1960s, I think. The machine learning is like 2010, right? And they're all the same thing, right? So more or less, except machine learning is going to use a computer and like an algorithm that loops through and optimizes the matrix of parameters that you have based on any input thing you can measure. Like what temperature is it outside, the humidity, if my dog barked today and things. Each one has a weighting parameter. You let the computer minimize that to your output, which is like the price of diapers. And then like, if it works, then you just go back and you can say, I can predict the price of diapers, or I can predict if my dog's going to bark, or whatever, it works forward and backward. So that's kind of the machine learning approach. And he's more or less using that in a simplistic way. Like he has just one parameter and he only has like 20 things. Like in machine learning, you usually have like thousands of things. Like there's a learning set, and then there's a prediction set. So you have thousands that you learn from, and you predict like 100. Right? He has like 20. He's going to predict. He's just going to show the curve that works for his learning set. So he doesn't actually. He kind of predicts. He kind of says like, well, we would want to have this length of side chain on it to make it have the glass transition that we want. So anyway, that's more or less where he's going with this. So it's almost embarrassing, like in a sense, like he isn't. So this guy's you read his book on polymer physics, and he's a scientist, he's a thinking person. Then he's going back to this grunt, like caveman technique, and he's saying like, look at how well it works. So it's kind of oddball. Of course, it's a group of people, so maybe he's just riding along with a pony cart, but who knows? Anyway, so he invents this method, and it reminded me of like, we used to play poker a long time when I was in grad school. And like there was one guy, Mike Sikowski, who had always, and he was retired from P&G recently, but every time, so you rotate like who was dealing that could pick the game. And he was always pick a game where there's like so many rules, like it's going to be high-low, split the pot. One-eyed jacks are wild. It's going to have 4 exchange rounds, so many rules that there's no possibility that anybody could, like he always won, because he made so many rules. So it's just like that here. He's going to take the polymer and he's going to say, oh, well, anything that's in the side chain I'm going to add is 1, and then anything in the main chain I'm going to add is something A times something. I'm going to decide the factor that the A times something is by an arbitrary rule. Then I'm going to end up with an equation that gives me this mobility, right? It has nothing to do with mobility. Maybe loosely has something to do with mobility, right? So end up with this equation, and these things are each calculated. I don't really understand this one, but somehow phenols are better than thiophene. So the sulfur 5-member ring, and then the phenols are aromatic 6-member carbon. So anyway, they have different mobilities based on that. And so he's at 1.2A for the relationship between those two. And then the carbons in the side chain are 1. So he adds them all up, divides by how many things he added, and he gets an average mobility for the thing. And that's where he gets this number that matches perfectly with TG for this set of things. It doesn't really mean that you can predict anything from it. It means you can match this set of things with that number. So it's impressive, but it's anyway. So that's more or less what's going on here. There's a couple other twists in here. So he has so the traditional. So he just said the side groups were a plasticizer to the polymer. Then there's kind of 2 approaches to that. There's so let's see. This is this thing I just added. I shouldn't have opened everything because you can't find it after that. Yeah, right. This is Flory-Fox, but anyway, so this is a classic Flory-Fox glass transition. So it has to do with the end, like we saw, like the end groups are more flexible, so they have a lower persistence in the middle. The middle's stiffer, right? So basically, if you think about that, that's like adding a plasticizer to the polymer. If you have short molecules, then there's a lot more plasticizer, and it goes with 1 over the number of end groups goes with per chain goes with 1 over the molecular weight. 2 over the molecular weight with the number of end groups. So that's how many end groups. It's a linear function that says those end groups are diluents, and they're going to detract from the glass transition by some constant, and then I can predict the glass transition as a function of molecular weight with that. And there's an infinite molecular weight when this term goes to 0. Right, so that's how the glass transition. That's the standard Flory-Fox equation. And in the paper, he says the Flory-Fox, but what he really means is are you okay with that?
No, I have a question.
All right.
So when you say plasticizer, is that like the
Dashboard of your car. like PVC is crystalline and you put plasticizer in it to make it into like pleather.
Okay,
Yeah, so it's just some kind of phthalate organic thing that gives you cancer.
yeah,
And it eventually leaches out and your dashboard cracks. And then you get cancer the next day. So, yeah, it's plasticizer's got kind of a bad name, but they're good things, you know. Anyway, you need it. You can't, all right. The reason you need PVC is because when you make caustic and AOH, so you have salt brine, right, from the underground of Louisiana and also in Michigan, which is why Dow Chemical was founded in Michigan, because there were brine mines there, or whatever, wells. So they get the brine, then you can separate it, and you make like, you can make HCl and NaOH with it, right? But you get like a lot of extra Cl. Like you don't, and the NaOH is like a major industrial chemical, and HCl's like sulfuric acid's more popular, put it that way. So you end up, so you don't use all the Cl, so you get tons of Cl. So if you go to like the Mississippi River, like Plaquemine, Louisiana, there's gigantic tanks of chlorine gas. If you go into that plant, like you have to wear a mask, and if the horn goes off, you're dead. You know, even with the mask, there's nothing because your skin will dissolve. Cl is bad, you know, like we used to do SiCl4, burn it, you know, to make silica. Everything in the lab was rusted, like inside where you opened up machines and way inside, and it's like all rusty, you know, so it's like pretty nasty. So you think HCl isn't that big of a deal, but the stuff that you get's diluted way down. It's like 2% or something in water, you know. Anyway, anyway, PVC is a way to dispose of Cl, because ethylene, you have tons of it, you burn it at the top of the distillation column, it's the flares. And then Cl, well, we got tons of that, like more than we need. I mean, you can make chemical warfare with it, you know. Other than that, there isn't much use for it. Right? So anyway, dumping all that Cl into plastic, and then everyone's happy with their pleather, that's like a sweet solution to a chemical problem, you know, problem of the industrial age, I guess. But anyway, there are side effects that you need to use plasticizers. So you just add a low molecular weight in to drop the TG so that it becomes flexible. Anyway, that's the Flory-Fox. So the Fox equation, so then says like Fox and Agua came up with this equation, which is an alternative to Flory-Fox, which is 1 over TG. And then they have molecular weight, same molecular weight dependence, but it's 1 over. And then this is positive instead of negative because it's 1 over, right? So then Fox came with this equation. It's called the Fox equation, which is different than the Flory equation. It's a 1 over TG, and then these are the mass fractions, right? So why the mass fraction is because the mass of the two things are different. You know, so if you did a mole fraction, so if you have some huge thing, a polymer, right? So there's one of them, and then you're going to have these plasticizers like benzene, and there's like a gazillion of them. Right? So if you did the mole, be a gazillion and one, right? So that wouldn't work because it would be all benzene. But the weight of benzene is about equal to the polystyrene or whatever, like napalm. So basically, you know, you're going to have a 50-50 split by weight, but by mole, it's going to be like 1 to 99, right? So anyway, you have to use weight here because of that, right? So it's kind of like weird that you use weight instead of moles to calculate kind of a thermodynamic parameter. I mean, this is an odd equation in that sense. Then the 1 over, why is this 1 over and not just a straight linear sum? You know, that's another question. So none of these are firm answers. I'm just making this up, but basically you could make up your own answer if you want. But basically, TG, I guess, as 1 over TG as something like the higher the temperature, the lower the frequency. So this is like a frequency sum almost, like high temperature, low frequency. So you're taking like a weighting of the frequencies, and TG has to do with motion. So it's going to have to do with frequency. So it kind of makes sense by that, not even a hand waving argument, that because the reason it's not a hand waving argument is the relationship between TG and frequency isn't 1 over, it's by the Arrhenius equation. Right? In other words, you have to have frequency equals exponential of the activation energy divided minus activation energy over KT. So it's not a linear, not an inverse relationship, but so you could probably make up your own Flory-Fox using the Arrhenius equation to relate the frequency to the temperature, and then write something more complicated than this. But it turns out this equation works great. Like it's 100% accurate. So no one's going to make up a new equation. but there might be an improved equation. Anyway, that's the argument for that equation, which is a question in the homework. So he does that. That's the Flory-Fox modified, except it's a weight of the side groups. He's saying the side group is a plasticizer, and then he's just getting the TG by this inverse sum weighted thing. By the Fox. Oh, he does say it's a Fox equation. I thought it said Flory-Fox, but so anyway, that's the whole story for that. When he does that, then he gets this plot. So this is the Fox equation plotted against weight of the side groups. And he claims he gets like two populations. One, I think, is a thiophene, so the sulfur ring with 5-member ring with a sulfur in it, and the other is the aromatic phenol ring ones. Right. So, and he gives an argument for why there's two classes of the things. And then he says, lo and behold, when he makes up his number, then those two join together and he predicts the actual behavior of the universe. Like he has the red and blue here from that business. It's a nice thing, and it all makes sense. Then he's pulling in the packing length because he's near Annandale, like he has packing length on his mind, whatever, or it's 2020, so it's like 14 years after Fetter won the Ford Prize. And this guy's in the APS Physical Society, so for whatever reason he puts it in here. And then he diminishes it, like he says, like, I think it's pretty good agreement considering it's also can predict the plateau modulus. So he doesn't pick up that it's the same dependence, or he doesn't note at least that it's the same dependence as the plateau modulus on P, like it's a cube, 1 over P cubed, right? So he never even mentions that. So, I mean, he could have taken this and driven down the street with it and then explain like why these things aren't the same. So why would the plateau modulus have to do with TG? So that's a question in the thing too. So actually it's a simple thing, but basically the questions I realized could be kind of difficult. So say you go up in temperature, so you're a glass down here, right? So, and then you go up here and it's a liquid, or it's a rubber. The plateau modulus is kind of at high temperature, right? So you're kind of looking at a plateau. So say in this kind of sigmoidal thing, right in the middle of that is where usually you define, there's 3 ways to define TG from this, right? The most popular way is find the middle of that sigmoidal. That's like, seems to be the way that everybody does it. He does it by looking at G double prime and there's a peak in it. And he says the peak is the glass transition. That's consistent with the Debye relaxation approach. And then the third way is to take the ratio of G double prime by G prime, you get tan delta. It's a tangent of the phase shift in the oscillating thing. It's like the stress and the strain are offset by an angle of the oscillation frequency. And that angle is delta, and tan of the delta is G double prime over G prime, and that ratio has a peak in it, and that peak is at TG. So like 3 ways, you get 3 different numbers, I think. Usually, if it's a nice system, like this black system, so the peak of that is exactly at the halfway point of that. But if you're at kind of a nasty one, well, this doesn't have even a sigmoidal because it never has a rubbery plateau. And then so he just takes it from that. So to be consistent, he always takes it from where that is. And this is a side group rotation with the TG for the side group, right? And each one of those would have kind of a relaxation time associated with it. So anyway, so if you raise the plateau modulus, that's going to shift the center of the sigmoidal over to the left. Like if you keep the solid part the same, and then the rubbery part. So this is a glass, like a glass marble, and then this is a rubber. If you lift the rubber part and keep the glass the same, which is no reason the glass would change, then that center point would shift to the left, and you lower the TG. So that's why the plateau modulus might be associated with shifts in the TG. Right, in perspective of this measurement, which is, so anyway, so there's a lot. I mean, if you look at it carefully or just kind of probe into this thing, there's a lot of things you could think about here. So what else is in here? So he mentions that the Debye-Waller factor, hopefully you can do that. Just fish around, like it's just 1 line, try to get, there's like 6 things to give 1 lines on, so 6 lines actually. Then figure 2 shows G prime, G double prime versus temperature determine the peak. Why does G double prime drop above the glass transition? Okay, so Just a couple of ways to look at that. Okay, so he shows that plot in here too somewhere. Oops. So one way is just from a so at this end, at the low temperature, you have a glass. So that's like a glass marble, right? So if you drop a glass marble, it bounces up. It's a Hookean spring. So it's a Hookean elasticity, right? So when it springs back, that's the modulus. That's the storage modulus, G prime. Whatever's left that it doesn't spring. So you drop your marble and it bounces up. The part that's left is G double prime. The part that it bounced up is G prime, right? So glass marble, it bounces almost all the way up. So there's not much G double prime, so it's low. When you get to the rubbery plateau, so if you have a rubber ball, which I brought one, I didn't have a glass marble, you bounce it and it also bounces up almost all, and there's almost no loss, right? So it bounces almost to where I dropped it from. So basically, on the high end, when you're in the rubbery part, it also has no loss. So glassy here, no loss. Rubbery here, no loss. I used to have was it neoprene or something rubber that had a glass transition at room temperature. You could just put it in like ice and it would be glassy. And then and room temperature would just be at the glass transition at that peak. What you find out is if you drop it, it's just like dropping a piece of lead. Like it just absolutely stops. Like you drop it and it's just dead. So it totally absorbs all the energy at the glass transition, right? So that's why it's got a peak in the loss and the storage is kind of dropping, I guess. So loss can be explained pretty easily by looking at things like a glassy marble, rubbery ball, and then the glass transitions in between where it completely absorbs all the energy. So that business is described by, so I put on some things from an old class here about, all right, so there's a DMA, there's a page from the company like that makes DMA that gives their explanation for whatever this is. So that might be more useful than me, but, and then this business of Dubai Relaxer, there's a paper, right? So the equation that goes with it is this, this delta E, so this is in terms of dielectric, but the same goes with complex modulus. So G equals, and it's got imaginary and a real component to it. So that's just if you plug in, if you have just a relaxation, exponential relaxation T over tau, then you plug in the dependence, the sign dependence of this oscillating thing, then you'll get that thing. It's a function of frequency. Or you can take this simple exponential decay function, which is called the Dubai exponential decay, right? So it basically you can take that and Fourier transform it and get this also change time into frequency. So either way, plug in sine of omega tau for the time dependence and you'll get this equation, or you can do a Fourier transform. It's the same thing. You can do a Fourier transform and get that too. So anyway, this is the governing equation for Dubai relaxer, which is just a thing that has one single exponential. So if you take that and you go, let's see. Here, I'll never turn this on. So you have the complex G is like G naught plus delta G over what, 1 plus tau omega. So tau is a relaxation time, and that's a frequency that we do in the dynamic measurement, right? And then I, and there's an I times that. So you have to clear the complex here, so you do a complex conjugate minus I tau omega, and then do the same thing up here. So that gives you G double prime, and this gives you G prime, right? So if you do that, the bottom's going to be, so this times that, I times I is -1, and then, so basically that thing gives you tau omega squared. And the ones give you 1, right? And the negative cancels out, so it's plus. And then the cross terms, 1 times that is minus, 1 times that's plus, so those cancel, right? So that's how you clear the complex. Then you get a number for the G prime plus this G naught. And then, because those are all real, and the imaginary part, which is G double prime, is the tau omega part. Okay, so if you look at that thing in terms of frequency, right, G double prime, you're going to find out that this thing, the numerator increases linearly, right? Tau omega, it's going to just increase, and the slope of that's tau. And the bottom part decreases because as omega gets larger, this will override 1. So that thing is going to decrease like that, kind of like whatever, something like that, right? So when you multiply those two together, you get this stuff. So at high frequency, it's a glass. At low frequency, it's a liquid. And then you have this magic number where tau equals omega, and that gives you the peak. You can figure out that would be, so when tau equals omega, this is 1 over like 2, 1/2, right? 1/2 I. Right, so you have that magic number where they match up. So you can plot that and you'll see you get the same, you get that thing. And that this place is where omega equals tau. That's the Debye tau d, the Debye relaxation time for simple relax. So you notice that everything Debye did follows exponential, like a single minus exponential to something. Like the Debye screen length is 1 over r, e to the minus r. It's always the same thing, you know. So all of his functions end up with like this exponential term in it. Completely different subjects, but you like that function for some reason. Right. So there's that. And then if you want to read more, there's like stuff about stuff from the old class, like dynamics, something, blah, blah, blah. You can read more stuff about it. There's like 3 or 4 links there. So hopefully that kind of answers that question more or less. Here. Why does it drop above and below? What happens to the TG that causes the peak? So at TG, you've reached that Debye relaxation time, or in this case, this relaxation time for 9 units of the polymer chain to like move in a coordinated fashion. That's what they define as TG for a polymer. 9 mer units moving in a coordinated fashion. I have no idea how they came up with that, but that's like a textbook reason. That's what the tau is, the relaxation time, when that moves in a coordinated fashion. And temperature is related to frequency by the Arrhenius equation. That's just the wait, I skipped. Anyway, the Arrhenius equation is this. So we have frequency 0, e to the minus tau, temperature to frequency, activation energy over KT. Arrhenius. Right, that's just the Arrhenius function. Right, so it's not a linear and inverse. It's that function, right? So then how's TG determined from the DSC measurement and supplemental? I said that like there's 3 ways to get it. The way he gets it is from the peak and the G double prime. Usually tan delta versus frequency, you get a peak. And then you can take it from that middle to sigmoidal. There's 3 ways to get it. The reason he doesn't use the middle to sigmoidal is because the signal is weak here. Like if you look at his curves, finding the sigmoidal for these doesn't work. And then in the DSC, the DSC plot of this thing. So the thermal screens. Yeah, sorry. All right, sorry about that. So DSC, so you put your stuff in a cell and you heat it up and you watch how much heat it takes to change the temperature of the thing, right? So as you're heating it up, so this is Q and that's T. dQ dt is the heat capacity. So you expect to see a straight line here. Okay, the heat capacity of a liquid is higher than a glass. So you expect to see a change in slope here. So it should go, and this is negative heat here, right? So it's going down because it's negative heat. And then you should expect to see it take a dive when you get to the liquid state, right? And that cutoff point will be the glass transition. But because it involves like motion, so basically it depends on how fast you move this, and there's going to be an overshoot. So you overshoot that crossover point, and that causes you to have this kind of knee to it. But taking the slope here will be the heat capacity of the glass, and the slope here is the heat capacity of the liquid, and the in between would be like the glass transition. They usually take like that other sigmoidal thing as being like the middle of that would be the glass transition for a DSC measurement. Anyway, so there's a lot here, I guess, but it's stuff you should maybe know if you took Polymer before or something. And I don't know, if you don't, you can learn it here or just kind of wing it if you can. Then like just take a look at what he did. I guess like that whole scheme of adding up the numbers and then it works in the end, but maybe you could say something about how if that's goofy or not, you know, like basically this question is, does that like, is that how you would approach to do this? You know, I mean, it worked what he did. You got a paper in Nature, but the whole thing is a little bit embarrassing to look at in a sense, you know, because just like, you know, it isn't anything, it's not really science what he's doing. It's just like add up the things. It's like what a chemist would do. Like a chemist, this is basically exactly what a chemist would do. Like they don't care about understanding what's going on. It's just like, here's the thing, I can predict the thing. That's it. You know, and then they're done with it. So
When he says like mobility,
Uh-huh.
is he talking about like just like the flexibility of the
yeah,
polymer?
but it doesn't mean anything. It's just, all right, he says mobility, but it doesn't mean anything. He's making up a number 1 for carbon. Like, what's that? That's not mobility. That's a number 1 for carbon. You know what I mean? When he says it's A times that number for a thiophene ring in it. I mean, that's also just like, that number is just found because it agreed with the results. Right? Like he's fudging the number to get it to agree with the results. And there's not any kind of reason why a thiophene would have lower or higher mobility than something else. It's just like that's what it worked out. So anyway, I mean, there's some understanding in it, but it's basically a little bit embarrassing, but it's good. Like the subjects here are good for us, I think. Like if we can figure out these, you can read a lot more papers. Everything's going to have all this stuff in it, you know, so you can see like the oscillating mechanical test that's in every paper, right? So the rheology, oscillatory rheology. So all those things are like repeated over and over again. So hopefully you can kind of just see. Anyway, we're out of time, so you can quit there. This is supposed to be a short one too, so it's like looks like it isn't that short.